Then we'll go from there. All right, so first 7 rows of Pascal's triangle. I'll give you the first 2. What would be the next row? 1, 2, 1. All right, they always begin and end with 1, and the middle, or the non-ending, beginning and ending values,
1, 3, 3.
are the sum of consecutive values, so 3, 3. So begin and end with a 1, and then take the sum of consecutive values.
1, 4, 6, 4, 1.
So that 1, 5,
10, 10, 5, 1.
and then finally
1, 6, 15, 20, 20, 15, 1. 20, 15.
all right. So we have our Pascal's triangle now. I mean, that's like minute math. Like, okay, cool. Now that we did that, let's learn something useful. No, we actually need that in order to find the derivative of more complicated functions, because if you don't have something like that, it tends to get out of hand pretty quickly. All right. The idea being that even if you're using the what I think is the easier limit definition of a derivative, you increase the powers, you're increasing the difficulty level. If you had a linear function, it wasn't too bad to come up with the derivative. Quadratic, there was a little grouping involved, but not too bad. Once you got to cubic and beyond, it started getting a little crazy. So let's see if we can figure something else out in terms of shortcuts. So first thing I want to do is remind you of what the other limit definition of a derivative is. So the limit as h approaches 0 of f of x plus h minus f of x, all over h. All right, that's one of the limit definitions of derivatives. All right. We worked with the other ones when we were doing it by hand. It's just that in order to develop the shortcut rule, this one ends up being a little bit more user-friendly. All right. Algebraically, we're going to do a little bit more work early on for these 2 examples, but the payoff is going to be that we're going to learn the shortcut, and then once we have that, then we don't have to do any of this anymore. You know, unless you're asked to on a test, in which case you use the other variation, the f of x minus f of a formula. All right. So find the derivative of f of x equals x squared using the limit definition and Pascal's triangle. So we have the limit as h approaches 0 of f of x plus h. So I need that. So they gave me f of x. F of x plus h would just be the same expression where we replace any x with an x plus h. Everything else should kind of work itself out. Because it's minus f of x. F of x is the original function x squared, all over h is built into it. So what I have to do here is expand out this in order to simplify. Now you could FOIL this out. You could take x plus h and multiply by x plus h and actually do the FOILing process. But we want to use Pascal's triangle. Pascal's triangle allows us to do the expansion without having to do any FOILing. The benefit is when you have something that's like power of 3, power of 4, power of 10 even, you're not foiling. All right. So what I want to do here is focus just on the relevant row. I almost said column. That would be this row. All right. So the coefficients of my expansion.
Do you know it's that row because it's squared?
We know it's that row because it's squared. Yep. So my coefficients are 1, 2, 1. So I'll write 1, 2, 1. When using Pascal's triangle, we take whatever the first term is in the binomial and raise it to the given power. So that's going to give us an x squared. And then working from left to right, we decrease the power by 1 each step of the way. So x to the first, x to the 0th. Then we take the second term.
Wait, why isn't it x squared plus h in parentheses squared?
Because when you evaluate a function, you're replacing the variable with what you're evaluating it for. So I'm replacing this x with x plus h.
Yeah, so wouldn't it be x squared plus h?
No. Because I'm taking, if I had something like f of x equals x squared, if I wanted f of 2, I would just take the x and replace it with the 2. If I want f of a, I would just replace the x with an a. This time I want f of x plus h. So I'm just replacing my x with an x plus h.
Oh,
It's just direct substitution.
gotcha.
Alright, so my second term raised to the second power in this case. That's what the function is going to end with, the expression is going to end with. So h squared, h to the first, h to the 0th. Alright, it's all positive, so I'm going to chuck some positive signs in there. Definitely a lot more stuff here than we need because a lot of this cancels out, but I'm just writing it all so you have good notes. Alright, so that all will be minus the given f of x over h. So I'm going to want to clean that up a little bit. All right, you can clean up and cancel on the fly if you want. So you'd have x squared plus 2xh plus h squared minus x squared all over h.
Wait, don't do those not cancel out the x squared.
Going to do that now.
Oh, okay.
So I'm going to kill the x with the negative x squared. So now I have 2xh plus h squared over h. Simplify. Nick's got a nice streak of texting while I'm in the middle of teaching. I think we're like 2
no,
weeks long.
I swear I was not texting. It was out, I know, but I wasn't texting.
You were, okay, whatever. I'm not going to get into it, but generally when a person's like wildly typing on their phone while giggling, I'm going to assume that they're probably doing something along the lines of possibly Instagramming or Facebooking, any of those possibilities. Let's not get too technical.
I'm sorry.
Anyway, 2x plus h. Now we can apply the limit because the troublemaker was the h on the bottom. The h on the bottom's gone because it divides evenly into each of the terms on the top. And now I can plug my h of 0 in, get 2x plus 0, which is just 2x. All right, so that's my derivative that we denote with an f prime. Generally, you could use the other notation, but this is the notation we're going to live with for the foreseeable future. F prime of x equals 2x. The other one is the dy over dx if you want that too.
You said that this way is not the shortcut, it's just like,
This is going to guide us to finding what the shortcut is.
So when you get where the denominator and that's when you can substitute? Like,
Yeah, only because if I were to substitute any earlier, I'd get 0 in the bottom of the fraction. Once the thing that makes it 0 in the bottom goes away, fair game. All right, so now something a little spicier. Find the derivative of f of x equals x cubed using the limit definition in Pascal triangle. Now you look at the work that we did here, it wasn't crazy, but it was a little time consuming. Not overly interested in doing that way too many times. Obviously this is going to be more complicated because it's a higher power. So what we want to do is use what we figure out from these two answers to help us come up with a generalization. All right, that's the idea. Discovery. The journey, not the destination. Well, I guess discovery would be a destination, but whatever. You get the idea. So limit as h approaches 0.
Plus h cubed minus x cubed.
Exactly, because if I take f of x plus h, I'm going to take my x and replace it with an x plus h. All right, so x plus h cubed minus x cubed over h. All right. Now we use Pascal's triangle to expand that because we don't generally want to take our answer from x plus h squared and FOIL that against x plus h. It's time consuming and there's not really much of a payoff. The payoff comes from using Pascal's triangle. So coefficients 1, 3, 3, 1. That's the next row down. Take the x, raise it to the third power. So x to the third. Reduce the power by 1 from left to right until you run out of power. Take the h, raise it to that power. Go from right to left. H cubed squared, h to the first, h to the 0th. Everything's positive on the inside. From that expansion, that lovely expansion, we're going to subtract off an x cubed. And divide it by h. All right. Now, in this step, you're more than welcome to cancel on the fly because 1x cubed h to the 0th is the same as saying what?
1x cubed.
1x cubed. So 1 positive x cubed. So this is the same, well, it's the opposite of this, so they'll cancel. And if you want, you can even divide out the h, but I'm not going to do that. I'm going to actually show the next step. So limit h approaches 0, 3x squared h plus 3xh squared plus h cubed over h. Now I could divide out the h. 3x squared plus 3xh plus h squared. Apply the limit. When you apply the limit, what do you get? Just the 3x squared. So f prime of x, or derivative, would be equal to 3x squared. Good stuff. All right. So we knew x to the second was 2x. We knew x to the third was 3x squared. Now, whether you verified it or not, you probably came up with x to the fourth being what? 4x cubed. Now, just to actually make sure that that's a tendency that will remain true in all cases, you may actually want to verify it for the next one, but you can also just take my word for it too. The idea is going to hold true because really we have a 2x to an understood first power, 3x to the second, 4x to the third, so 5x to the fourth, and so on. All right, so what we want to do is generalize that because we want some kind of idea to come across that gets us from here to here, gets us from here to here, gets us from any original function to its derivative without having to find the 7 that came before it.
I think I have it.
Okay.
Is it nx to the n minus 1?
Nx to the n minus 1. Okay, we can take that. So I'm going to make a kind of a new expression in here. Let's say we just had x to the nth, but no a value there, no coefficient. If that's the case, then it would be nx to the n minus 1. I agree with that completely. Yeah, because you're taking whatever the n value is, you're sliding it down to become the coefficient, and then you're reducing the power by 1. Right? But in math, we can't just slide things. There has to be some sort of mathematical operation involved. Right? So if I told you that there was an understood coefficient in front of this that's a 1, what was the operation that made this 1 into an n? Operations being addition, subtraction, multiplication, or division. So which one happened here in order to make this 1 into an n? Multiplication. Okay, so we multiplied the power by the leading coefficient and reduced the power by 1. So then it begs the question, could the same thing happen if the coefficient was something other than 1? And we don't really have any examples on this page that'll tell us yes or no. All right? So at this point, we can only really just kind of make an educated guess and say, all right, well, if that's the case, if this is a constant coefficient that we call a constant multiple, because it's the multiplier of the function, then we'd be looking at, if we're following that idea, n times a x to the n minus 1. All right, so we're taking the n and multiplying it by whatever the coefficient is, still reducing the power by 1. So on the next page, what we're going to do is we're going to see if that holds up in all cases. That being said, you can use your calculator to get a quick and easy verification. So in y1 in our calculators, put in your original function. In y2, put in what you think the derivative is. And we're going to put an expression in y4. We're going to skip over y3 because later on in the course we're going to use that for something else. All right. So I'll just grab one at random here. Not really random. Not how randomization works. I'll take the x to the 5th. I'll take the 5x to the 4th. So the corresponding derivative. Now you see what I have there in y4? We haven't done that yet, right?
No.
Hi, excuse me. Yep, he's next door.
Student just has to get something. Thank you.
All right, so that expression is a really important expression because that means the derivative of whatever I have in y1, so I'll show you how to put that in. Oh, they use parentheses. The rest of humanity uses brackets. All right, so let me take that from scratch. So in y4, you're going to hit math 8. All right, so it's the same way to bring that expression up, but we're just going to do something different with it. Math 8.
Thank you.
No problem. So when you hit math 8, this expression comes up. So in the field y4, so skip over y3, hit math, scroll down to 8, or hit the number 8. It says n deriv, but it brings this up. The first entry should be an x, so type in an x. I want it to point to y1. Y1 we get by hitting alpha, trace, and selecting y1. So alpha, trace.
Y1, enter,
Y1, then enter.
and okay, and then X goes up.
And I want it to have x equaling x at the end. What that means is that I want the calculator to graph the derivative of whatever I have in y1 for any value of x. Alright. If my y2 and y4 are the same as one another, then I know that I have the correct derivative. So this is, again, for all x. It's a good way to check your work. So I don't need to see y1, because that's the original function. I'm just comparing y2 and y4. Just a question of, do you want to go by the numbers, or do you want to go by the graph itself? If you want to go by the numbers, just hit second graph, go into your table. It really doesn't matter what the scale is. You're comparing y2 and y4 to see if they're the same. Okay, maybe it doesn't matter what the scale is. Okay. With an appropriate scale, because those were like obscenely small numbers, you can see that y2 and y4 are virtually identical, maybe a little variation at 0.
What is 1e minus 12?
0.0000000000001, which is essentially 0, right? I think it's more satisfying when you actually see the picture. So what I recommend you do is first, under y4, hit enter on that slashy thing. So hit the left arrow till you get to the slashy thing. It'll make it bold. So that'll plot y2 with a regular type of curve, and y4 it'll make it darker. And then I'm going to hit enter on the equal sign for y1. That's going to turn it off. So then all I need to do is just graph it, hopefully with a reasonable window. I'll do a zoom 6, hope it works out. Alright, there's my original, not my original function, but it's what I think the derivative is. And here's what the calculator thinks the derivative is. We both think it's the same thing, so I'm pretty satisfied that I didn't just screw that up.
Go down to Y4 and switch over to Y5.
I'm going to do that again in a second. So if you're a little behind, you'll get caught up in a sec. Here's a quick example. Let's say you have a function f of x equals 2x to the 4th power. What's the derivative going to be? 8x to the 3rd is what we think it's going to be based on that rule, because we're taking the power, multiplying it by the coefficient, and reducing the power by 1. All right, so that's my suspicion. Let's see if my suspicion is accurate. So I'm going to put in my original function, 2x to the 4th. I'm going to turn off that equation by hitting enter on the equal sign, because I don't want to see the original function. Then I'm going to type in my derivative function, what I think it is, 8x to the 3rd. y4 I can leave alone, because all it's going to do is take whatever I put into y1 and graph the derivative of that. So if that matches what I have in y2, I'm in good shape. So I'll try standard zoom. It's possible that it won't be a good window. In this case it is. But if it's not, you may have to play around with the window. As long as bold traces over, not bold, you're pretty satisfied that what you have is the correct derivative. So now what you have is an answer key, basically a walking answer key. It doesn't really walk though. I'm still working on that. I haven't figured out the programming.